Hi Oslo! Jeg er Dave Aronson, T-rex fra Kodosaurus, og jeg fløy hit på Kjeledermi pterodactyl for å lære deg om genetiske algoritmer. Men jeg skulle gjøre det på engelsk. Mainly because you've just heard almost all the Norwegian I speak. So, what are genetic algorithms in the first place? The concept as a whole is an optimization meta-heuristic, which is fancy talk for a kind of shortcuts to find good solutions to some problems. Ideally the best solution, but we'll usually have to settle for something good enough due to constraints like time or money. There are many kinds of such optimization heuristics, but what makes genetic algorithms unique is that, as you may have guessed from the name, they are inspired by real-world biological evolution, primarily the principles of survival of the fittest, random combination of different sets of old genes, no, not like these, into new ones and random mutations. The history goes back to about 1950, when Alan Turing, as in Turing test, Turing machine, Turing completeness, and so on, proposed a learning machine in which he figured that the mechanism of learning would be something similar to evolution. Nothing much ever came of that approach to machine learning, and it took a few decades for genetic algorithms in general to get much serious traction. But in the late 1980s, the first commercial product based on genetic algorithms, a mainframe toolkit for industrial processes, came out from General Electric. And in 1989, a genetic algorithm toolkit called Evolver came out for PCs, as those were the hot new thing at the time. These days, systems such as MATLAB have some genetic algorithm routines and functions and such built in, and most major programming languages have some kind of genetic algorithm libraries or other such packages available. But the actual usage of genetic algorithms still remains mostly obscure, used by companies internally for their industrial processes, logistics, and scheduling, and so forth. But once in a while it does get used for something a little more interesting and more publicly known. Most famously, in 2005, NASA used a genetic algorithm to design the antenna for its ST5 series of satellites, which then got launched in 2006. No, that's not just a paperclip that got bent up by someone sitting fidgeting in a boring meeting. The NASA Jet Propulsion Laboratory website says, "Its unusual shape is expected because most human antenna designers would never think of such a design." And that is one of the great advantages of this approach. These algorithms are much less hampered by any expectation of similarity to previous solutions. However, today we'll only be looking at much simpler problem domains for the purpose of making understandable demos. So how do genetic algorithms work? Most people, upon hearing about them, think, oh, that must be terribly complicated. But they're not really. They consist of a series of fairly simple steps. First, we create an initial population of candidates. In genetic algorithm lingo, these are generally called chromosomes, but since every living thing contains lots and lots of chromosomes in every cell, I don't like that term. I think it just leads to confusion. So I'm just going to call them candidates. I've also heard them called individuals or solutions or phenotypes, to use another actual genetic term, but most people don't know that one, so yeah, I'm going to ignore that one too. The next step is to assess the fitness of each of these candidates according to whatever criteria we want to apply. We do it at this point mainly because it supplies the data usually used in the next step, which is to ask, are we there yet? I mean, are we done yet? This is usually based on the fitness, but could be based on other criteria. We'll see some of those later, or a combination of both fitness and other criteria. Assuming we're not yet done, then next we select some breeders to use in actually breeding the next generation. And this is also usually based on the fitness to simulate survival of the fittest. After that, as you may have guessed, we then use those breeders to breed the next generation. And some of the previous population, particularly the fittest ones, may be carried over into this new population, but usually not. Next is a very important but unusual and easily forgotten step when you're talking about it, which is to mutate those new candidates so we get some more diversity in the gene pool. And finally, we go back to assessing the fitness of these new candidates. And this sequence could be represented at a very high level with some fairly simple code, like so. And this happens to be in Ruby, which I chose because it reads fairly close to just plain English. So even those of you coming from like Java or F# or whatever, you'll probably understand that. If not, well, I'm hoping that the surrounding verbiage will at least convey the general concepts. Now let's take a closer look at what goes on at each step by working through an example. First, we create an initial population of candidates, but what is a candidate and how do we create one? These are different solutions to some problem, like the shape of an antenna, and can be represented usually as different instances of the same data structure. That can be any data structure we want, so long as we can feed that to functions that will evaluate the fitness and combine old ones into new ones and mutate them. The simplest common type of candidate is just a string of bits. And this will do fine for candidates that consist of a series of yes-no decisions. That may sound simplistic, but there is a huge category of problems that boil down to this, called knapsack problems, which is a category of constrained resource allocation problems. The canonical example is that you have a knapsack or rucksack, backpack, whatever you call it, and a bunch of different things that you want to carry in it. But they won't all fit. Or maybe it totals up to more weight than you personally can carry. Or maybe both. Or sometimes there's other constraints. So we want to find the combination of items that will fit in the backpack but has the maximum value. And that could be the literal cash value, as in the example we'll get into in a moment, or something more metaphorical. To look at a concrete example, suppose we know a farmer with a smallish truck, and he needs to decide what to take to the market once a week. And on this farm, he has some cows, E-I-E-I-O. So among the things he can take are cows, milk, cheese, butter, ice cream, meat, and leather. And for the sake of simplicity, we won't differentiate between price and profit or between meat and dairy cows. And he always has the exact amount on hand, and he can only take a specific set amount of each thing. Now his truck has room to take all these items, but it can only take so much weight. So that's going to be our constraint. His choices are as follows. And you don't need to memorize any of that. Just notice that it totals up to 8,600 pounds. But his truck's suspension can only handle 2 tons. In other words, 4,000 pounds. So let's see what happens if we use a genetic algorithm to evolve a good enough truckload. First, we need a way to represent each candidate, in other words, each truckload. And in Ruby, we could just make it a class with a constructor like this. Oh, that looks like we're just creating a random number. That's right, we're creating a random number with 7 bits, 1 for each item, thus yielding a random 1 or 0, indicating whether we take that item or not. And we could get as complex as we want in this function, like requiring a minimum or maximum number of items per truckload, but we're just going to keep it simple. To create an initial population, we can just create a whole bunch of these truckloads and stuff them into an array or other such container structure like so. And this could actually be done with much more idiomatic Ruby, so those of you who know Ruby, please don't scold me for this. I'm just trying to keep it very broadly understandable. So if we create an initial population of 10 truckloads, it might look something like this. Now, why 10? Because that's what fits on the screen in a decently readable size. If I were doing this for real with a more complex domain, I might use 100, 1,000, 1,000,000, whatever. But how did we get from those random numbers to these combinations? Behind the scenes, such a translation might look like this. We have a list of items that we could take, each described as instances of a generic item class. And to check what's in our cargo manifest, we can just loop through them and see if the corresponding bit is on. I'll skip over that code just to keep the code in this presentation simple. Now that we're done with the initialization, we assess the fitness of each of these candidates. So we do this with what's called a fitness function. Surprise! And just like how biological creatures might be a perfect fit for one ecological niche, but a lousy fit for another, this needs to reflect exactly what purpose we're applying here. And, you know, in this case, we want the cache value. However, any load that's too heavy for the truck is totally worthless no matter how much the value of those items would total up to. So in Ruby, that could look like this. We iterate through the item numbers, summing up the weights of the things we want to take, and the bit on function is left as an exercise for the reader. And if that exceeds the truck's capacity, we return 0, else we use the same technique to sum up their values. Again, we could get as complex as we want in this function, and NASA's antenna fitness function certainly must have been. For instance, if the truck was a little smaller and couldn't physically fit everything, and we had the volume of every item, we could total those up and make sure that that particular truckload will physically fit within the confines of the truck. Anyway, if we run this on our current population, we get this. Nothing you need to memorize, except notice that the best one scores 20,000. So now that we've assessed their fitness, we check, are we done yet? But what are our criteria? This function can be quite simple, but it can take some thinking to figure out exactly what it should do. With a knapsack type problem, a very good solution, even the absolute best solution, can then be made absolutely worthless by adding just one more wafer-thin item and thereby exceeding the constraints and making it totally undoable. So what we're going to do is record the best we've seen and say that we're done if we haven't seen anything better within 100 generations. Why 100? Pretty much random. It seemed like a good chance for improvement, and since our functions are simple and our population is small, it's not going to really take all that long. And in Ruby, that could look like this. When this code is initially parsed, we set the best truckload we've seen as an empty one, and the count of generations since we've seen it as 0. And then when we call the function, We increment the number of generations, look at the fitness of each candidate, select only those that are better than our current benchmark. If there are none, we return true if it's been at least 100 generations since we saw the best one, because that is our agreed on definition of done. Otherwise, we return false. But if there is at least one truckload in the current population that is better than what we've recorded as the best we've seen so far, we take the best one, make that our new benchmark, and reset our count of generations. And return false to say, no, we're not done yet, we're starting the whole 100 generations over again. And once again, we can get as complex as we want in this function, like checking not only the maximum fitness, but maybe the minimum fitness, the average fitness, or a couple of things not having to do with the fitness at all, like some maximum number of generations, or time, whether watch time or CPU time, or letting the user press a stop button, or any combination of things. But as far as our code goes, I'm just going to keep it simple. Now, since this is the first cycle through, we're obviously not done, so next we select some breeders with which to breed the next generation. And the obvious way to do that is to take the top two most fit. We take the population, sort them by fitness descending, take the first two. Pretty simple. Out of our current population, that would get us these two. And as usual, we could get as complicated as we want in this function. One other common way of selecting the breeders is what's called roulette wheel selection, in which each candidate has a chance to be chosen proportional to their fitness, and then we randomly find some spot on the roulette wheel, see whose variable size wedge that falls into, and there's lots of other ways. We could also take more than two, whether to breed all pairs within that set or to breed more than two at a time, because these don't have to follow the same rules as biological organisms. Or we could even combine such things like breeding all trios out of a set of 4 chosen by roulette selection. Now that we've chosen our breeders, we actually breed them. And the usual way is something called crossover, and that consists of taking the data points, or in genetic algorithm terms, the alleles, from one parent up to some randomly chosen crossover point, and then we start taking them from the other parent. And again, this could be complicated further. You could use multiple crossover points, especially if you're using more than 2 parents. But we're not going to do that. We're just going to use one, like so. We establish the crossover point for each new candidate as a random number between 0 and however many items we have inclusive. We iterate through them. If we haven't hit the crossover point yet, we take it from the first parent, else the second parent. So that means it could all get copied from the first parent or the second parent, or it could switch over at some point. And if we do this once with a randomly chosen crossover point of 3, that gets us a result like this. And I've colored the ones from the first parent in green and the second in red to show the mixing. And this is just one of 10 results because we're making a whole new population, like so. And you may notice that this is almost exactly like how we created the initial population. The only difference is that now each candidate is the result of breeding our 2 chosen breeders, as opposed to making it from scratch. And the resulting list might look like this. You can see lots of family resemblance there. None of these truckloads includes a cow, butter, or leather, and they all include cheese. And that's because both of our breeders were like that. If we were to just continue breeding the best of each generation, we would never see any loads that contain a cow, butter, leather, or no cheese, but we fix that in the next step, which is to mutate them. And again, I'm going to keep it very simple. I'll just give it a 1 in 4 chance of flipping each gene, and in code that would look like this. We iterate through the item numbers, and if a random number from 0 to 3 is a 0, we flip that bit. As usual, we could get as complex as we want, like having some genes more likely to mutate than other genes, or having a minimum or maximum number of mutations per candidate, or all kinds of other complications. If we run this on our current population, we wind up with something like this, where the green color means that it changed. You can see that we now do have truckloads that contain a cow, butter, or leather, or no cheese. So now we go back to assessing how fit each of these candidates is, and we couldn't do that until after the mutating, because the mutating would change how fit each candidate is. If we sort on fitness descending just to make it easy to find the best ones, we wind up with this. Oh no! Our maximum fitness actually went down. As you may recall, our previous best one scored 20,000. Now we're down to 15,000. But don't worry, as you may recall from our "Are we done yet" function, we hang on to the best one and just try to outdo it. So we haven't lost it. It's fine. The next generation might look like this, a small improvement over our previous best. So we set that top one as our new benchmark, reset the generation counter, and start trying to outdo that within 100 generations or more. And if we let this run to completion, we might wind up with something like this, with our best truckload scoring 26,000 points, made up of cheese, meat, and leather. So that's one complete run of a genetic algorithm. And if we wanted to make sure whether this was the best that this algorithm could produce, we could just run it again, and again, and again, as many times as we like, within reason, because it's so much faster than brute forcing our way through the whole solution space or precise calculation. Now, that might not actually be true when we have such simple criteria, only 7 items, 1 truckload a week, but if we were choosing from among hundreds of items for several truckloads a day, variable amounts of different things on hand and more complex criteria, then yes, writing a genetic algorithm would probably be well worth it. Now suppose we want to evolve something completely different. Suppose we want to evolve a good set of stats for a Dungeons & Dragons fighter character. So our candidates are going to be tuples, or if you prefer, tuples, of numbers, rather than strings of bits. And D&D character stats are strength, intelligence, dexterity, constitution, wisdom, and charisma, each determined by rolling a set of 3 6-sided dice, or 3d6. I'm going to gloss over how you can sometimes have extra strength. In Ruby, that might look like this, with the roll function left as an exercise to keep this code simple. So our initial population might look like this. Next, we assess how fit each of these characters is. And we're trying to evolve a set of fighter stats. So this should be based mostly on the strength, the constitution, and a little bit of dexterity, but the intelligence and wisdom, charisma, not so much. But we don't want them too low because of occasional saving throws. I tried several different things, like initially totaling up double the strength and the constitution and half the dexterity, but the other stats tended to get too low. Even the dexterity was suffering pretty badly, so I tried prioritizing them linearly, adding up 6 times the strength, 5 times the constitution, and so on, down to 1 times the charisma. But then the other stats got too high and the characters seemed too generalized. I finally settled on prioritizing them much more strongly with a geometric progression, totaling up 32 times the strength, 16 times the constitution, and so on, down to 1 times the charisma. And this illustrates how the fitness function may be very simple, but it can take a lot of thinking and experimenting and so forth to come up with one that will yield just the right mix of alleles, especially in ones that are not considered immediately important. Anyway, if we run this on our current population, we get this. Now we can ask, are we done yet? But what are our criteria? Let's say we're done if any character scores 90% of the total maximum possible value of our fitness function. And I'll spare you the math, but that would be 1,021. And in code, that would be fairly simple like this. None of our current candidates score anywhere near 1,021, so we're not done yet. So we next select some breeders to breed the next generation. And I'm going to stick with just taking the top two most fit. In this case, that would get us these two. And the abstraction now gets a little more obviously leaky now, because we're totally ignoring the issue of sexes. We have no guarantee that these two are going to be a male and a female. That's not even part of our data. And we had the same leak last time with the truckloads, but since it wasn't as relevant, I let it slide for the moment. Now that they're actual living human beings, well, imaginary, but still, whether they're elves or dwarves or whatever, we could add that factor in, and many other complications such as compatibility and so on. And that could complicate our selection function enormously, possibly even make it impossible to find a viable pair among such a small population. Anyway, next we actually breed our chosen pair. And this time I'm going to use a slightly different strategy, which consists of essentially flipping a coin, or as we used to call it, a D2, for each gene, like so. We go through them one by one, flip a coin. If it comes up heads, we get from the first parent, else we get it from the second parent. And that could get us a result like this. And again, this is just one of 10 results. And the whole new population might look like this. And there are two things to notice here. First, the number of red and green is not always the same, neither within an individual nor in the whole population. It's a series of random coin flips, so on average it's going to be 3 and 3, but it could be anywhere up to 6 to 0 in either direction. Secondly, once again, we have some pretty strong family resemblance. For each stat, once again, there are only two possible alleles, two possible values, or in genetic algorithm terms, alleles, for each gene. Now that was true before because we were only dealing with true, false, yes, no, whatever you want to call it. But now we have the whole range of numbers from 3 to 18, so it's a little more concerning. And there would be only one possible value, and therefore half as many possible combinations, if any stat were the same between the two parents. At a glance, these look on average much more suitable as fighters than our previous generation. We'll figure their actual fitness in a moment. If we were to just continue breeding the best of these, we'd never see any change in the possible values for each stat, in other words, the alleles for each gene. But again, we fix that in the next step, which is to mutate them. And again, I'm going to keep it simple and just give each gene a 1 in 3 chance each of staying the same or going up a point or down a point within the valid range of 3 to 18. And in code, that would look like this. For each stat, we add a random number from 0 to 2 and then subtract 1, which is effectively the same as adding a random number from -1 to 1. And then we clamp it within the range of 3 to 18. As usual, we could get as complex as we want. Maybe do things like let it have a higher chance of going up or down if it was very low or very high, possibly by multiple points. And that would help simulate the real-world phenomenon of regression to the mean. If we run this on our current population, we wind up with something like this. where the green means it went up and the red means it went down. And looking at the values in each column, you can see we now have much more diversity. Now we go back to step 2 and assess the fitness of each of these candidates. If we sort on the fitness descending, just to make it easy to find the best, we wind up with this. Now it's easy to see that this generation is much improved over the previous one. The old one ranged from 476 to 760, and the new one goes from 635 to 851. It's still nowhere near our stopping criterion of 1021 though. So fast forwarding through several more generations, we finally get one suitable character having 18, the maximum strength and constitution, acceptable though kind of subpar dexterity, and surprisingly high intelligence. That's not a problem, but it is a bit of a waste. If we really wanted it more specialized, we could complicate the fitness function even further and do things like explicitly demand well above average scores in each of the class's primary useful stats and forbid it to be so high, or at least apply a penalty in the class's less useful stats. So now we've evolved a set of fighter stats. Let's suppose we don't need any more fighters in the party, but now we want a wizard. All we need to do is tweak the fitness function like so, to prioritize now intelligence, wisdom, and dexterity, and so on down to strength. And an initial population would look roughly the same since we haven't changed how that's generated. So I'll spare you those steps, but after 11 generations, I finally got this, with 3 candidates, 90% fit to be wizards. They're mostly pretty good in the other stats, but oh, what happened there? Okay. Alright, they're mostly pretty good in the other stats, but not so much as to be obviously better suited for some other class, though that top one looks kind of like a good bard to me. Remember though that this is all very random. It might converge more quickly or more slowly, and the fitness function may be good or poor at getting just the right mix of alleles. Now suppose we want to evolve yet another kind of thing. By the rule of 3, it's time we extract the common parts into something that they can all use, something with a name like, oh, say, Evolver. That's my actual license plate, by the way. I've had it for several years, since long before I ever got into genetic algorithms, and I used that name for the code I've been showing since before I ever heard of the Evolver PC toolkit that I mentioned near the start. Anyway, with just a little bit of tweaking and a slight sprinkling of Ruby magic dust, we can create a class that will define the common parts and accept another class to define the varying parts and run evolution on it, like so. No, I don't expect you to read all that at once. We'll go through it piece by piece. Since it's meant to accept a class and hang on to it for later reference, we can use a constructor like so. It just stashes that class, and just for fun, also an option for how big a population to use. And how we tell it to run evolution can look like this. Just a slight variation on our original high-level code. Mainly, we're passing the responsibility for determining whether we're done, selecting the breeders, and mutating each candidate over to the class that got passed in and stashed. And we're also sorting them on descending fitness just for convenience. Creating the initial population could look like this. Again, nearly identical to our original code, but passing the responsibility for creating each individual candidate over to our passed-in class. Breeding a new population could also look very similar, but passing the responsibility for combination over to the passed-in class. So with this evolver class handling most of the infrastructure, we don't need to repeat most of the boilerplate that we had in the truckload and character classes. And we can demonstrate that by evolving something else and supplying only the parts that vary. So what now? In my spare time, I make mead, a wine-like drink made by fermenting honey. Let's see if we can evolve a good recipe. Our recipes will be based on two simple factors: the ratio of water to honey and the alcohol tolerance level of the yeast we'll use to ferment it. The resulting percent alcohol by volume, or ABV, and the sweetness will be how we will evaluate the recipes. But I'll spare you the details of how we get from those inputs to those outputs. If you really want to know, catch me during the hallway track or party or whatever, and I'll talk your ears off about making mead. Beyond just creating the recipes, we'll need a way to evaluate their fitness. And this one looks at how far off we are from some target values. We do a little bit of fancy math to keep them both close rather than trading one off directly for the other. And you can see here that we're targeting 12% ABV out of a range of typically 0 to about 20 and 15 points of sweetness. What is that? Well, that's on sort of a custom scale like this. 0 to about 60 or 80 for anything reasonable as a finished product. Explaining this chart is, again, beyond the scope of this talk, but catch me later and I can tell you all about it. Anyway, this means we're going for roughly typical wine strength and semi-sweet. And we'll stick with the breeder selection function of just taking the top two most fit, but we'll also need a combiner function. And that could look like this, sticking with the tactic of flipping a coin or rolling a D2 to see which parent contributes which gene. Once each candidate combination is created, we'll also need a way to mutate it, such as this. And what this does, put briefly, is to let the stat go up to 19% up or down. Everything else, such as creating the initial population, selecting the breeders, breeding a new population, the concept of how to check if we're done, though now with a different threshold, and the overall structure of how it simulates evolution is handled by the evolver class. And to use the evolver class and the recipe class together would look as simple as this. This would return the current population of recipes when the recipe class says, yeah, it's done. And to demonstrate briefly how it might evolve mead recipes, an initial population might look like this. And yes, we can have negative fitness. It's usually the order that matters. The next generation might look like this, with slightly improved fitness and a narrower range of fitness. After 7 generations, I got this, just a little bit weaker and sweeter than I wanted, but within the 90% fit criteria. If we got really picky and demanded a 99.9% fit, or as SREs would say, go from 1.9 to 3, my first run like that took 45 generations and yielded this, a tiny bit weaker and sweeter than I asked for. Now, just like the Dungeons & Dragons characters, if we want something different, all we have to do is tweak the fitness function. So I tweaked that to ask for 7% alcohol and only 5 points of sweetness. A low alcohol dry mead, often called a session mead, and still demanding a 99.9% fit. It took only 37 generations to get this. Spot on in sweetness and just a tiny bit weaker. Then I asked for 16% alcohol and a sweetness of 35, way beyond what I actually like. A strong and sweet mead, historically known as a sack mead or great mead, a style very popular in Poland, the largest producer of mead these days. That took 149 generations, but that was still very fast because the population was so small and the functions were so simple. to produce this, just a tiny bit stronger and drier than I asked for. There are many other ways we can use genetic algorithms. They can produce images and music and even code. So think about it, and there might be some way that each of you can use genetic algorithms. To recap what you've learned here today, genetic algorithms are optimization heuristics, which is fancy talk for shortcuts to finding a good enough solution to some problem. They're simpler than you probably thought. All you need to do is create an initial population and cycle through 5 fairly simple steps until you're done. They can use very simple functions, but it can be tricky to figure out exactly what those functions should do, especially for evaluating the fitness and figuring out if we're done, so as to make the solutions converge quickly enough, but not ignore too many other very good solutions. This approach is applicable to a huge variety of problems, including ones so complex that a semi-random algorithm can come up with very good solutions that we humans would never have thought of. Now, if you have any questions, I'll take them now or at that contact information up there. As for the other URLs, the first one at GitHub is for all the code and the slides in HTML, CSS, and JavaScript because I'm using Reveal. And the second one is, as you may have guessed, for the slides in PDF, complete with a script, which I've more or less stuck to. So, any questions?
Yes, me. How different is this algorithm from machine learning or deep learning neural networks? I see many similarities.
Okay, how different is this from machine learning, deep learning, neural networks, and so forth? He sees many similarities. Unfortunately, I am not that familiar with deep learning, machine learning, neural networks, etc. Some people would consider this a form of machine learning, so you could say that maybe Turing was a little bit right. But I, for one, do not really consider this to be machine learning. It's not really learning to do anything. It's not understanding anything. It is just tweaking data. Like I need to tweak how these windows are set up or something. There we go. That derailed my train of thought. If I were more well-versed in AI and such things, I could possibly draw some more parallels. But the main thing that springs to my mind, at least, is that with at least my understanding of machine learning and so forth, you wind up with a trained model that will do better and better. Whereas with this, you run the algorithm again, it might come up with something better, but maybe not. It's not generally going to be influenced at all by having run it before. Yes?
Is overfitting a problem?
Overfitting?
Yeah, is that a problem?
Is overfitting a problem? Oh, interesting question. I have heard that discussed in the context of machine learning and so forth. I suppose one could overcomplicate one's fitness function and thereby dictate the alleles of the candidate more than one should. For instance, if we were to try to deliberately overfit a fitness function for Dungeons and Dragons fighter characters. Okay, it's got to be 18, 18, 18. I forget what sequence they're in, but 18 strength, constitution, dexterity, and let's say 12 or 14 or something in the others. And yeah, that's going to drive the results to be closer and closer to that. But if you want to use a genetic algorithm, chances are you're not going to be using something where you can so precisely predict, what your absolute ideal is going to be. Would it be a problem in a more complex domain, like, say, antenna design? I could see it possibly being, but I'm not familiar enough with that sort of domain to see how that would apply. So the short answer is, I don't know, but I guess theoretically it probably could be. Any more questions? Going once, going twice. Okay, looks like we get about 4 minutes of our life back. Thank you. Thank you.